Hello, in this video we're going to go over some properties of ionic compounds, and then we'll talk about some special cases for ions. So we've mentioned a few ionic compounds at this point. We've seen, for example, NaCl, MgBr2, AlCl3, etc. And those look like really simple compounds. However, ionic compounds exist as alternating positive and negative ions in regular three-dimensional arrays. So these are called crystals, and in particular, we would call this arrangement of ions a crystal lattice. So sodium chloride has a more simple crystal lattice since there's just a 1-to-1 ratio of sodium ions and chloride ions. So you'll notice here in this picture we have alternating blue and green ions. So the blue ions are sodium, the green are chloride ions. So really, it's not just one sodium ion and one chloride ion. We actually have this whole arrangement of alternating sodium and chloride ions. So when we write NaCl, we're really just talking about the simplest ratio of ions. And this makes sense, right? Because sodium chloride is table salt. When we shake salt over our food, it comes out as tiny little crystals. So if we were able to actually zoom in on those crystals, we would be able to see the alternating ions. Now, each individual pair is called a formula unit. So again, this would be the simplest ratio of ions in a crystal. So if we were to zoom in on a crystal of magnesium bromide, we would see that there's a magnesium ion surrounded by bromide ions, and they're arranged in a way where the simplest ratio is 1 magnesium ion for every 2 bromide ions. Same thing for aluminum chloride. We would see the simplest ratio, or the formula unit, is 1 aluminum ion for every 3 chloride ions. So here we can actually see some crystals. These are more complex crystals than the ones we just talked about. But we have, for example, amethyst, which has a really beautiful purple color. We have cinnabar, which has kind of the same color as cinnamon, right? It's sort of a brownish color. Azurite has a blue color to it, and then vanadinite has more of an orangish color. But you'll notice that each of these crystals have very distinct shapes, and that's due to the arrangement of ions in the crystal lattice. So amethyst, we've got kind of triangular shapes going on. You can sort of see those there, kind of around. And then cinnabar, we have these really nice long shapes. Azurite has almost square shapes going on. And then vanadinite sort of has the same kind of rectangular or square shapes in its crystals. Now, those different colors are usually due to transition metals. So the ionic versions of transition metals. So things like iron, manganese, vanadium, etc. So the part of the periodic table we don't normally deal with, the middle of it, but we do get these really interesting colors from those ions. So let's talk about some properties here. So ionic crystal lattices are really strong. So those positive and negative charges are very attracted to each other. So it takes a lot of energy in order to break that bond, that ionic bond. So for example, if we wanted to melt an ionic compound, we would need a really large amount of energy. So just imagine you pour some salt into a pan and you want to melt that salt, that table salt. It's probably going to take quite a bit of energy to melt it, but that's true for any solid, right? It takes a lot of energy to melt a solid. So sodium chloride has a melting temperature of about 800 degrees Celsius. So it takes a lot of heat, a lot of energy. However, let's say we apply a physical force to a crystal, to that ionic compound. They are going to break really easily. So even though ionic compounds have really strong attractive forces, they're very brittle. So if we hit a crystal with a hammer, the crystals are going to shatter pretty easily. Another characteristic property of ionic compounds is their electrical conductivity. So for example, here we have a little experiment where on the far left we have just a sample of water. And in that water, we've placed some electrodes. And the electrodes are connected to a battery on the right. And then on the left, that battery is connected to a light bulb, which again is going to connect to the other electrode. So typically when we want electricity or a current, we need an exchange of ions. Now, water does not have any ions, or at least not a large amount of ions in it. So water, since it's a molecule of H2O, it's neutral, so again, no charges. So we're not going to see that exchange of ions between the electrodes. So we don't have a current and the light bulb does not light up. Now, let's say we just put those electrodes in a sample of table salt. So this is just salt in here, so just a solid. Nothing's going to happen because the salt is still in its crystal form, so there isn't going to be an exchange of ions because the ions can't move around. They're stuck in place in their crystal lattices. But let's say we dissolve that table salt into a cup of water. We know that salt can dissolve in water. And what happens when it dissolves is the positive ions and the negative ions can separate. And that's due to their attraction to water, which we'll talk about more later. So that means the sodium ions and the chloride ions can move around in that water solution, right? So the positive ions are going to be attracted to the negative, to the negative electrode. So let's say that's the one on the right. And the negative ions are going to be attracted to the positive electrode on the left. And that's going to cause a current to form and to run through those electrodes and through the battery, through the light bulb, and we'll see that the light bulb actually turns on. So when ionic compounds are dissolved in a solution, we do see electrical conductivity from that solution. All right, so now that we've talked about some properties of ionic compounds, let's talk about a special type of ion called a polyatomic ion. So far we've just looked at single atom ions, right? So sodium plus, chloride minus, But some ions can consist of multiple atoms, and then those multiple atoms have an overall charge. So what's really happening is those groups of atoms are covalently bonded. So they're sharing electrons with each other, but they have an overall charge. So for example, this first one here that's listed in the table below is the ammonium ion, which is NH4, and it has an overall +1 charge. So I'm going to draw NH4 here for you, and we'll learn more about how to draw these later. But nitrogen is surrounded by 4 hydrogens, and then this entire thing has a +1 charge. So this would be a polyatomic ion because it has a charge and it contains multiple atoms. So you'll notice there are a lot of polyatomic ions. We also have the hydroxide ion, which is OH, and that has an overall charge of -1. The cyanide ion, which is a poison, that has 2 atoms that have an overall charge of -1. And then we have the carbonate ion, which is 1 carbon and 3 oxygens, and that has an overall -2 charge. Now, we can also add a hydrogen to that, so that would give us the next one, bicarbonate, or you could also call this hydrogen carbonate, and that just has a -1 charge instead of a -2 charge. There's also the acetate ion, which comes from acetic acid, which is vinegar. And there's a couple different ways that you can write that formula there, but it has an overall -1 charge. And then we have nitrate, sulfate, phosphate, and chlorate. So I do highly recommend memorizing each of these ions and their names. So know their formulas, their charges, and the names, because we're going to see these quite a bit going forward. So I do have flashcards on the Canvas website. They should be under modules, flashcards, or on the main page of the website. So definitely start memorizing those because, again, we're going to see a lot of compounds that contain these polyatomic ions. So let's actually look at one as an example. So the rule here for constructing formulas for ionic compounds that do contain polyatomic ions is exactly the same for, or as what we've already been doing with single atom ions or monatomic ions. So we want to make sure that the positive and the negative charges balance each other. So let's look down below. Let's say we want to write the formula for barium ion and the nitrate ion. So barium has a +2 charge and nitrate has a -1 charge. All right, so I can already see that we probably want to multiply the nitrate ion by 2 so that we have 2 negatives to match the 2 positives that barium has, right? Okay, so let's write Ba, and we only need 1 barium, so we don't have to write a subscript for that. But NO3, we have 2 of those. But if we write a subscript 2 next to NO3, it looks like we have 32 oxygens, which is not the case, right? So how can we make sure we don't confuse anyone? Well, what we can do is put parentheses around NO3, which is the polyatomic ion, And then we'll put a subscript 2 outside of the parentheses to show that we have 2 of those NO3 ions. So again, NO3 is our nitrate ion, and then the 2 tells us the number of nitrate ions. So again, if you have multiple polyatomic ions in your formula, put parentheses around it before you put your subscript in, because otherwise it'll look really confusing, like in this case where it looked like we had 32 oxygens. All right, so let's practice. Let's determine the ionic compound formula for the following. So ammonium and nitrate, magnesium and phosphate, and sodium and carbonate. So let me just write down those polyatomic ions for you because I know you couldn't have possibly memorized them in the last minute. So ammonium is NH4 plus 1, and we just saw that nitrate is NO3 minus 1. Magnesium. What charge does magnesium have when it's an ion? So remember, magnesium is in column 2 or group 2. So it has 2 valence electrons, and it wants to lose those 2 valence electrons to become like a noble gas. So if it loses those 2 electrons, it's going to have a positive 2 charge. And then phosphate is a polyatomic ion, whereas magnesium was a monatomic ion. So phosphate is PO4 minus 3. And then we already know that sodium has a plus 1 charge when it's an ion. And then carbonate is a polyatomic ion, and its formula is CO3, and its charge is minus 2. So see if you can match the charges together and write out the formula for each of these ionic compounds. All right, so let's see if we have the same answers. So it looks like in number 1, ammonium and nitrate, their charges are going to balance. We have plus 1 and minus 1. So we can just write that as, oh, my iPad wanted to zoom in. We can just write that as NH4NO3. And we don't need any parentheses because we just have one of each. So we just write them right next to each other. Now, what about magnesium and phosphate? We have a plus 2 charge and a minus 3 charge. So remember my trick from the last video, we can just multiply each by the other's charge, right? So let's multiply magnesium by 3. And that means we'll multiply phosphate by 2. So 2 times 3 gives us 6, and 3 times 2 gives us 6. So we have plus 6 and minus 6, so that will match. Perfect, so that means we have multiples of each, but magnesium is a monatomic ion, so we don't have to put parentheses around magnesium. There's no confusion there. If we put a subscript 3 next to magnesium, we just know right away we have 3 magnesiums. However, if we were to write PO4 and 2, it looks like we have 42 phosphates or oxygens in our phosphate. And that's not correct. So we want to put parentheses around PO4. Okay, so now the last one, sodium and carbonate. We have +1 and -2. So how do we balance those charges? Well, we could multiply sodium by 2, and that will give us an overall +2 charge, which will match the -2 charge on carbonate. So again, sodium is a monatomic ion, so we do not need to use parentheses with sodium. And then CO3, we just have one CO3, so we'll just leave it as it is. But again, it is really important to memorize those polyatomic ion formulas because that way you can recognize when you do have a polyatomic ion, like carbonate or phosphate or nitrate. So definitely make sure to look at those flashcards. You can even write your own if you would like. Now, one last thing I want to cover in this video. What if you have an ion and you don't know its charge? How can you figure out its charge? So some metals can form more than one ion. So for example, iron. Iron can form a +2 charge and a +3 charge. It just depends on what it's bonding to. So sometimes it can give up 2 electrons and sometimes it can give up 3 electrons. Now, this typically only happens with transition metals and a couple of other metals on the right-hand side of the periodic table. So, for example, if I draw a little periodic table here, we've got our transition metals in the middle. So kind of right in here, there are some metals that have more than one charge. And there are actually a couple kind of in this area too on the bottom right. So all of the other metals and the nonmetals will have just one charge. So, sodium, magnesium, everything in group 1, group 2, and then the nonmetals, those all just have one charge. But in the middle of the periodic table is where things can get kind of strange, which is why we don't cover it that often. However, iron is a really common ion, so we do need to know what charge it has. So let's say you're told that you have the compound FeCl2, but you don't know what the charge on iron is in this compound. How can we figure that out? Well, luckily, it's bonded to a nonmetal, and that nonmetal chlorine only has one charge when it's an ion. Okay, so do you remember what the charge on the chloride ion is? -1, right? So we saw before chlorine has 7 valence electrons, which means it wants to gain 1 electron to become like a noble gas. So if it gains that 1 electron, it now has an extra negative. So it's going to be a -1 ion. Now, we do have 2 of those. So let's just write down a picture here. We've got 1 chloride ion, 2 chloride ions in our ionic compound. So that's an overall -2 charge. But it looks like we only have 1 iron ion. So what is the charge on that iron ion so that we balance the charges? Well, it has to be +2 to balance the -2. So let's just make a note. The charge has to be +2 to balance the chloride ions. Okay, so that's one way that you can figure out what the charge of a particular ion is. So let's practice. Let's look at some examples. So we're going to identify the charge on the metal ion in each compound. So remember, the metal ion is always listed first. So in the first one, we have copper, which has the formula Cu, and that is a metal ion that could have multiple or variable charge depending on what it's bonded to. In the second example, we have tin, which is given the symbol Sn. So we want to figure out what is the charge on tin, because that can also have variable charge. And then in the last example, we have lead, which has the symbol Pb, which stands for the Latin name plumbum. That's one of my favorite original element names, plumbum. But anyway, that can also have variable charge depending on what it's bonded to. So see if you can figure out the charges on each of these metal ions, knowing the charge on the non-metal. So you can pause the video, and then when you're done, you can unpause and we'll go over it together. Okay, so let's look at the first example. So copper is bonded to oxygen in this case. And oxygen always has the same charge when it's the oxide ion. So what is the charge on oxygen? So if you were having trouble figuring that out, you can always go back to the Lewis diagram. So how many valence electrons does oxygen have? Well, it's in group 6, so that means it has 6 valence electrons. And that also tells us that it wants 2 more electrons to become like a noble gas. So if we add in those 2 electrons, it now has an octet, but we also added 2 extra negative charges. So it has a -2 charge. Now in our first compound here, we just have 1 oxygen. So we also have 1 copper ion. So what is the charge on copper in order to balance the charge on oxygen? +2. Great. So actually copper can either have a +1 charge or a +2 charge. It just depends on what it's bonded to. So in this case, it was bonded to oxygen, which has a -2 charge. So that means copper has to have a +2 charge in order to balance it. All right, let's look at tin. So in this case, tin is bonded to 2 oxide ions. So let's just write that out. We have, oops, that's a little messy, but we've got 1 oxide ion and a second oxide ion. So that gives us a total of -4 coming from those oxide ions. And we only have 1 tin ion. So what is the charge on tin in order to balance the oxide ions? +4. So tin can have either a +2 or a +4 charge, And again, it just depends on what it's bonded to. All right, let's look at lead. In this case, lead is bonded to 2 chloride ions. And what is the charge on a chloride ion? So remember, chlorine is in group 7, so it has 7 valence electrons. And that means it just needs 1 more electron to have an octet. And if it has 1 extra electron, that gives it a -1 charge. And we have 2 of those. So let's draw both. Oh, whoops, my pen decided to stop working. Let's see if I can get it to work here. There we go. All right, so we have a total of -2. So what is the charge on lead in order to balance that? +2. All right. So lead is kind of similar to tin. It can have a +2 or a +4 charge depending on what it's bonded to. So in this case, since it was bonded to 2 chloride ions, it needed a +2 charge to balance the chloride ion charges. All right, so one last thing here. Let's name each of those compounds now that we know what the charge on the metal ion is. So typically, we would name something like NaCl as sodium chloride. So we end the negative ion with IDE. So we might think that the first one would be copper oxide. However, remember, copper could have a different charge depending on what it's bonded to. So we actually have to indicate what the charge is on copper. So we said that the charge was +2. So what we're going to do is after copper, in parentheses, we're going to put a Roman numeral 2. Okay, so for tin oxide, we have to do the same thing. So we have to indicate what the charge on tin is, otherwise we might get confused about how many oxygens are bonded to tin. So tin, we said, had a +4 charge in this compound, so we're going to write a Roman numeral 4 after tin. And then in the last example, we said lead had a +2 charge, so we're going to write that as lead 2 chloride. All right, and then if it's been a while since you've thought about Roman numerals, or if you've never learned Roman numerals, 1 is just 1 line, 2 is 2 lines, 3 is 3 lines, 4 is a little different. We're going to put 1 line and a V, and 5 is a V. So then 6 is a V and 1 line. It's good to know these Roman numerals. You don't have to know all of them. Most of the time the charges will be 1 through 6. They usually aren't anything bigger than that. So as long as you know the first few Roman numerals, that's all you need to know. All right, so let's summarize ionic compounds. Again, there are 2 ways to recognize an ionic compound. So compounds that exist between a metal and a nonmetal are usually ionic. So that's a key one. If you see a metal and a nonmetal, that's ionic. So for example, sodium and chlorine. Sodium is a metal, chlorine is a nonmetal. The second way to recognize an ionic compound is if you recognize a polyatomic ion in the compound. So for example, let's say we had sodium bonded to nitrate, NO3. This is a polyatomic ion, so that's another way to recognize that you have a ionic compound. Now, what if a compound contains two nonmetals? Well, that's going to be in the next chapter, chapter 4. But we have one more thing to cover in this chapter, and we'll cover it in the next video, and that's how to calculate the mass of an ionic compound. So I will see you then.